Hello there. Welcome to this new video. In this I will be talking about alkenes, so carbon-carbon double bonds, and we'll be talking about alkene stability, hydrohalogenation reactions, mechanisms. We'll look at energy diagrams, thermodynamic parameters, and something called Markov-Nikov's rule. Enjoy! I've told you about cis and trans alkenes, but we have to use a different designation when we have alkenes with 3 or 4 different groups attached. And in this situation, we're going to use the E or Z notation instead of cis or trans. Cis and trans only works if there's a hydrogen on each carbon of the alkene, because it essentially means the non-hydrogen groups are either oriented cis or trans to each other. So if you have more non-hydrogen groups, you have to use the E or Z notation. So the way we are going to do this is we're going to use our prioritization.
She needs to sort out her priorities.
Just like we did when we were assigning R or S configuration to chiral centers. And we're going to do this one carbon at a time. So we'll look at the right carbon and then we'll look at the left carbon. So you're going to assign priorities to each carbon of the double bond. So for this carbon on the right, when we go one atom out, nitrogen has a higher atomic number than hydrogen, so this group we consider to be high priority, this group we consider to be low priority. When we look at this carbon on the left, we've got fluorine versus carbon, one atom out. Fluorine has a higher atomic number than carbon, so fluorine is the high priority group, and the ethyl here is the low priority group. If the high priority groups are on the same side of the double bond, it is Z. And if the high priority groups are on the opposite side, it is E. So here, this was the high, and this was the high. So this would be E. And here, the high groups were on the same side, so this would be Z. And I like to remember this as Z for the same side. So again, this just shows you how you have the higher priority groups opposite to each other, and that gives you the E double bond. And if they're on the same side, it gives you the Z double bond. And then when you name these things, we actually want to incorporate the E or the Z designation in parentheses at the outset of the name. Now try this. See if you can assign EZ stereochemistry to this alkene. So I'm going to start with the carbon on the right and look at what it's attached to. So one atom out, I get to 2 carbons, so I have a tie. So now I look at what those carbons are attached to. This carbon's attached to 3 hydrogens. This carbon's attached to 3 oxygens, because we think of a double bond to an atom as counting twice for that particular atom. So this would be the high group, high priority. This would be the low. Now if we go over here, one atom out, we have carbon versus carbon, we have a tie. So then we look at what those are attached to. Here, this is attached to 3 hydrogens. Here, this is attached to 2 hydrogens and a carbon. Carbon beats hydrogen, so this is the high priority group. This is the low priority group. So if the high priority groups, we cut this double bond here, the high priority groups are on the opposite sides, so this would be the E alkene. E and Z alkenes are stereoisomers, but what type of stereoisomers are they? I want you to discuss in the chat these 2 questions. First, are they conformational or configurational isomers? Why would that be? Second, if you think they are configurational isomers, are they enantiomers or are they diastereomers? Why? Please discuss your thoughts in the chat. Now don't forget that there is restricted rotation around carbon-carbon double bonds. That will help you determine if these are conformational or configurational isomers. Now let's move along to the stability of alkenes. Cis alkenes are more stable than trans alkenes. And the reason for this is that there is steric strain, which is shown with this space filling model. So these methyl groups can actually bump into each other, and that won't happen in the trans orientation. In addition, the more substituted the alkene, the more stable it is. What do I mean by substitution? So I mean how many groups other than hydrogen are attached to the alkene carbons. So here this would be monosubstituted, because if we look at the carbons of the alkene, the carbon on the right has 2 hydrogens, the carbon on the left has 1, and then it's attached to 1 non-hydrogen group, so it's monosubstituted. Here, these carbons, I'm going to draw on the hydrogens. Each carbon has a hydrogen attached and 2 non-hydrogens. And overall, there are 2 non-hydrogen groups, so this would be di-substituted. So the mono-di-tri refers to how many non-hydrogen groups are directly bonded to the alkene carbons. Now, the more substituted the alkene, the more stable, which is due to something called hyperconjugation, which is quite complicated and involves some molecular orbital theory, which we don't really want to get into. But essentially what's happening is electrons in carbon-hydrogen bonds overlap with something called an antibonding pi molecular orbital. And this is a picture here. But essentially, when you have alkyl groups on your double bond, it allows for this hyperconjugation, which stabilizes the molecule. This is an energy diagram for the hydrogenation of cis and trans 2-butene. Hydrogenation just refers to taking the double bond to the alkane. So if you had trans 2-butene, you add hydrogen and some catalyst like palladium, and then you get the saturated alkane. Same thing with cis 2-butene. So the important thing I want you to see from this is that the trans stereoisomer is a lower energy than the cis stereoisomer. And that can actually be determined by doing this hydrogenation reaction and figuring out how much energy is released. Because if the final point is the same, they're making the same product, if the energy released is different, then the energy of the starting things must have been different. And so chemists have been able to figure out the heats of hydrogenation for a variety of alkenes by doing the hydrogenation reaction and then measuring how much heat is released. And if you see here, the more heat released, the less stable the starting material. So ethylene, which has no substitution, is less stable than monosubstituted alkenes, which are less stable than di-substituted alkenes. And notice cis is less stable than trans. And di-substituted alkenes are less stable than tri-substituted alkenes, which are less stable than tetra-substituted alkenes. So essentially, by doing this hydrogenation reaction and figuring out how much heat is released, we can figure out the relative stabilities of the starting alkenes. Choose the more stable alkene from the pair and discuss your answer in the chat. Again, discuss your answer in the chat, choosing the more stable alkene from the pair. So pause the video and evaluate these different alkenes. So a pi bond is an electron pair donor. It can act as a base by reacting with H+, and it can also react as a nucleophile by reacting with an electrophile. So you can have addition and elimination. In this chapter, we focus on addition. In addition, you start with an alkene and you end up with a carbon-carbon single bond in the product, but it has 2 new bonds, one to this hydrogen and one to the X, which just stands for a halogen. But the reverse reaction can also take place. And these are actually equilibrating reactions, and which side is favored depends upon the temperature. So remember our delta G equation, where delta G is equal to delta H plus minus T delta S? Well, addition reactions are favored by enthalpy. That's because the 2 new sigma bonds that you form are stronger and more stable than the pi bond that you broke. However, addition reactions are not favored by entropy because two molecules are combining to form one product, which is going to result in less randomness and less disorder. At lower temps, enthalpy dominates and addition reactions are favored. At higher temps, entropy dominates and elimination reactions are favored. So if we want to do the addition reaction, we want to do this at low temperature. Hydrohalogenation is just the specific name for adding HX to an alkene. Hydro refers to the hydrogen, halogenation, that refers to the halogen that you're adding. So here we're starting with an alkene starting material, and we're ending up with a new carbon-hydrogen bond and a new carbon-bromine bond. So if I put my hydrogens in here, my new carbon-hydrogen bond I can draw in here. So that hydrogen corresponds to that hydrogen. The mechanism is a two-step process. In the first step, the alkene grabs an H from HBr. So you draw an arrow from the center of the pi bond ending at the hydrogen. And then that HBr bond breaks and the two electrons in it stay behind with the bromine. And then you get to your carbocation intermediate. Now the carbocation in the next step is going to be the electrophile, and the bromide is going to be the nucleophile. So now the nucleophile attacks the electrophile, so it's going to donate its 2 electrons to that carbocation. And then you get your product. So I'm going to show you an animation here of the alkene reacting with HCl. So there, now we've seen that the pi bond grabbed the hydrogen, forming a carbocation, and now you have this negatively charged chloride hanging out. So the chloride in the second step is going to be the nucleophile, the carbocation is the electrophile. And that nucleophile is going to be very drawn to that positively charged carbon. So there it goes, it adds in, creating the carbon chloride bond. If the alkene is not symmetrical, then 2 regioisomers are possible depending upon which carbon gets the H and which carbon gets the halogen. So how do you know where does the X go and where does the hydrogen go? Well, it turns out that there is regioselectivity for what's called Markovnikov addition. In 1869, Markovnikov observed that the H atoms tend to add to the carbon that already had more H atoms. So in this example, you see that this carbon of the alkene had a hydrogen directly attached. The other carbon did not. And the new hydrogen from the HBr ended up on the carbon that had more H's to begin with. And the bromide ended up on the other carbon. So the halogen will be installed at the more substituted carbon. So here we see another example. So this 2-methylpropene, when you react it with HCl, you form this product, not this product. So here, the carbon on the right is the one with more H's. So that's the carbon that gets the H from HCl, shown in this intermediate. And then the chloride of the HCl gets added to this carbon, the one with less H's. And here yet again is another example. So between these 2 carbons, this one has an H, the other one does not. So the H from HBr goes to that carbon, whereas the bromide gets attached to the other carbon. Now why is this? It has to do with hyperconjugation again. And without getting much into it, essentially the more substituted carbon, the carbon with more carbons attached, when it's positively charged, is more stable than a carbon that has hydrogens attached. Now, can you predict the products of the following reaction considering Markovnikov's rule? Pause the video and see if you can do this on your own. Okay, so first notice that this carbon has 2 H's, this carbon has no H's directly attached. So we know that the H is going to add such that it goes on the carbon with more H's. Let me actually put that in a different color. Here, I'll put it in green. So here's my new H in green. And now I'll have a positive charge on the other carbon. That's my carbocation. So this is my intermediate. And now I have bromide floating around that's negatively charged. So it's now going to be my nucleophile in the second step, and this is my electrophile. So now it's going to add into that carbocation, so it will donate its 2 electrons, and then you form this product. The Markovnikov product is formed because it will proceed through a lower energy transition state. And the reason that is lower in energy is because the more substituted carbocation that's forming in the transition state is more stable. So remember, the height of that hill tells you how fast or slow a reaction will be. So since the hill is smaller, when you are on your way to forming the tertiary carbocation, that will occur faster. And that's why you get this product selectivity. So now consider this reaction. Choose the product from the choices shown here and discuss your answer in the chat. There is one other wrinkle to talk about, and that's the fact that when you do these reactions, you might actually form a chiral center, a carbon with 4 different things attached. And if you do that, you would form both enantiomers. So for example, with this reaction, you form a chiral center. So the H goes on this carbon of the HCl because that corresponds to the carbon of the alkene that had more hydrogens to begin with. And then the chlorine goes on that carbon. And so you end up with this chiral center. That carbon has a methyl, an ethyl, a chlorine, and a hydrogen. And you'll get both the R and the S configuration out. So the reason why you get both enantiomers has to do with the carbocation intermediate and the fact that it has this empty p orbital. So a carbocation is sp2 hybridized and it has an empty p orbital. And the halogen can attack from either face, and depending on which face it attacks from, it will give either the R or the S configuration, but there's nothing that will make it favor one face or the other. So there's an equal probability that you'll get the R versus the S. And then you end up with a racemic mixture, which means a 50-50 mixture of both enantiomers. Now practice on your own. Choose the products of this reaction. It could be one or more products. And discuss your answer in the chat. So in summary, we discussed that if the high priority groups are on the same side of the double bond, you get a Z geometry. This is the same side. If they're on opposite sides, you get the E geometry. And alkene chemistry is dominated by electrophilic addition reactions. We've just seen one type here called the hydrohalogenation. We're going to see more. And then Markovnikov's rule predicts that the H adds to the carbon that has more H's to begin with in the alkene. And then the X goes on the other carbon.